name's Ben Stopford. I work at a company called Confluent Inc. Confluent is the company that sits behind an open source project called Kafka. Kafka is a sort of message broker, which is quite useful if you have large amounts of data or you need to ship large amounts of data around a company or for a particularly high volume use case. Prior to that, I did a number of jobs which involved data at some degree of scale. And this talk is going to really concentrate on some of the kind of fundamentals of scaling data platforms, but both from a sort of relatively low level right through to sort of larger constructions, larger architectures. And the views here are expressed in my own. This talk actually predates Confluent, but you'll probably see there's some Kafka-esque stuff in here, which hopefully you'll find interesting. So when we think about data, actually really a lot of what we're doing is just really arranging for locality. And we're arranging for locality so that we can get sequential addressing. So that's to say that if we can arrange our problem such that all of our data is nicely placed in a contiguous form, then pretty much whatever media we're in, we're going to get very good performance. And there's a good reason for this, and it's that computers are very good at predicting sequential workloads. And the reason for that is because of the many levels of caching that exist, right through from the CPU to the disk buffer. So if we can arrange our data such that it's sequentially, such that it is a sequential workload, we can get very good throughput. And this is nothing, no media is this more apparent than on a magnetic drive. So I guess there's a well-known theory or intuition that disks are slow. And disks are, in some ways, slow. Specifically, they're very slow if you address them for random operations. But if you address them sequentially, they're actually pretty good. So if we take the example of a standard magnetic hard drive, we'll get maybe 200 megabytes per second. That's actually relatively conservative if we're addressing something sequentially. So be it read or writes. It'll be slightly different between the two, but it's pretty much the same. If we sort of scattergun the hard drive, we'll get maybe 300 reads per second. So for a sort of typical 100-byte row in a database, that's going to mean that it's about 7,000 times faster. So suffice to say that we have a great incentive here to arrange for locality, to arrange for sequential addressing. And this isn't actually, this property is ubiquitous. It doesn't have anything specifically to do with magnetic hard drives. It's available, it's present in every single layer of the stack. So a sort of slightly random coincidence is if we, on most modern hardware, if we address RAM at random, so we address, let's say we're using a garbage collected language, which will often place data around the address space, and we scan across that, and we think that we may be doing some form of sequential addressing, we'll actually be skipping all over the address space. And that will actually be about the same performance as reading sequentially from disk, which is slightly unintuitive in some ways. But again, it's just because of the levels of caching, or more importantly, that if we have a random workload, we just can't take advantage of these various different levels of caching because there's no predictability to it. So let's think about this problem from the concept of a very, very simple database. So the most simple database is a file. A file's kind of actually quite a nice abstraction in many ways. We can write to it very quickly if we append to the end of it. That's going to give us like 200 megabytes per second on a sort of standard magnetic drive, much faster if we're using PCIe. And we can there's a couple of ways that we might read efficiently from that file. So we can scan it in its entirety. That would be very efficient. Or we could jump to a particular position, this particular offset, and we could scan from there. And that would also work well, obviously because of the sequential thing. But we want to avoid this idea of scattergunning our address space or hard drive or whatever media we're using to try and avoid, or at least to keep our performance optimal. So let's think a little bit about how reads and writes to a file might work. So if we're thinking specifically about writing, we have basically two options. So if we want to do an update, we can append it to the end of the file. And in this case, version 2 is effectively replacing version 1, which was written earlier. And that would mean that we would be able to get very good sequential I/O, very good sequential performance, but we have this problem that we've got like effectively a orphaned value further back in time. Alternatively, we could do what a sort of traditional database would do and update in place, assuming we have fixed width fields, where we would just obviously jump into that particular position and update the value to be the thing that we wanted it to be. And this second approach obviously is going to imply some degree of random I/O and the performance impact that goes along with that. So a file is useful as a sort of useful abstraction for certain use cases, specifically anyone that's actually would necessitate a table scan. So many analytic workloads actually necessitate a table scan anyway. But generally, we want to do something a little bit more useful. We want to be able to support some kind of lookup. And the way we're obviously going to do that is with some form of index. So in this case, we've picked a sort of a tree-based index. Obviously, we could also use a hash index. We could use a bitmap index. It doesn't really matter. We could actually just use the values with the offsets in a sorted file. That would work equally well from a read perspective. But our index is effectively just going to we'll have the values that we want to look up and some pointers into a heap file. And this is kind of nice because our heap files can now be append only, and we can use the index sitting on top of that. But the problem with adding an index is that whilst we'll have the nice sequential I/O on the heap file underneath, the index provides an overarching structure. That's its whole point. Its whole point is to make it easier for us to read things quickly. So we need to update him effectively in place on the index, and that necessitates random I/O. So we're back to like scattergunning the file system. So that's slightly unfortunate. We had this kind of nice sequential use case that worked really fast, and now we've got something that's a little bit slower. And this is why if you use a relational database, or actually any database, and you're used to putting lots of indexes on a table, you'll often find that things tend to slow down from a write perspective. It's this reason. So there are three basic options there are many options for getting out of this problem, and we're going to talk about three of them. And those three are kind of three ends of the spectrum. And there are some other ones in between. But I think they're useful ones to think about. So the simplest one, and this is the one that actually most databases do, is to avoid this problem of random writes when we change stuff in our index by sticking the index in RAM. So that's pretty obvious, right? It's a very, very simple approach. And that has some pros and some cons. And one of the reasons for thinking about this is that when we relate this to different technologies, so different technologies basically take different approaches with respect to their storage engine. And their storage engine, and according to which choice they make, they're going to have very different properties. So most notably, this will work very, very well if you can fit all your indexes in RAM. Okay, that's kind of obvious, right? As soon as you've got a workload where you have more indexes than you do have RAM available, so this is typical of sort of big data use cases, then the indexes are going to start to page to disk, and things are going to run much, much slower, because we're going back to that world of random I/O, 7,000 times slower. So this is a good, simple option for relatively small data sets. So what else can we do? So another thing we can do is, so bear with me for a little bit. We could try this other thing where what we do is, as our writes come in, we're going to batch them up, and then we're going to sort them into a little index file, and then we're going to store that little index file on disk. So we're going to get a batch of writes, sort them, put them on disk. And then we're going to get another batch of writes, and we're going to sort them, and we're going to put them on disk. And what we're going to create is a set of small index files. So these could, again, this could be some sort of tree-based form. Normally, actually, it's just a sorted list of key value pairs, known as an SS table. But this approach has some sort of interesting side effects. So intuitively, it's a bit of a strange thing to do. So we've created lots and lots of small index files. Each of these index files we can write very quickly to the file system because each index is sequential. It's a sequential write. But we now have many different index files that we would need to consult if we wanted to do a read. So if we want to read from this structure, if we want to, let's say we want to read a particular value, we would have to basically consult each one of these index files and ask it, do you have this value that I would like? So it turns out that we can use some quite nice little tricks to optimize this approach. So we can, firstly, we can keep some sort of low overhead metadata in memory, which gives us some idea about what values are inside each index. Another approach which is used quite often is a thing called a Bloom filter. Anyone familiar with the Bloom filter? We've got a few. Okay, cool. So, I mean, Bloom filters, like, it sounds complicated. It's actually really simple, but it's a probabilistic data structure that you can basically tune to some probability, and within that probability, it will tell you whether or not a key exists inside effectively one of these files. But the main point of it is it has a very low memory overhead. So the sort of nice thing about this is that we've sort of changed this model to be something that's write optimized rather than being read optimized. So with this like set of small index files, and then we've used some tricks to optimize read. So what we've actually done is we've shunted that problem of random I/O away from the read concern and onto sorry, the other way around. We've shifted that problem of random I/O away from the write concern and onto the read concern. And the reason for doing that is that in the read concern, we can optimize that better. It's very hard to optimize away random writes. So what we've invented here is a thing called a log-structured merge tree. And this is the disk structure that backs basically the storage engine in most sort of big data tools, so Cassandra, HBase, LevelDB, RocksDB, etc. So in a log-structured merge tree, we have this collection of small indexes rather than one big overarching one. And we have an append-only structure. So we need to do a little bit of work to solve the problem of orphaned updates, but we can do that again with sequential I/O. And then we use this trick of like low memory indexes to increase our read performance. So ultimately, we're shifting this problem of random access on write onto the read concern, which we can optimize better. So that's kind of nice. So we have a couple of options. We can just put our index in memory. We can use something like a log-structured merge tree, which will basically shift the random I/O problem from writes to reads. What else could we do? Well, another storage engine approach, which is quite popular, is effectively brute force. So if we think back to that original file, it's really just solving that problem of like, I've got a use case where I kind of have to read a whole load of this data. So how do I optimize that problem? So the column approach is quite interesting. So traditionally, a database will hold data row by row in a file. That's like how they work, that kind of heap file. In a columnar database, you'll actually split the row into a whole set of files, one file per column, as the name suggests. So A ends at all of the versions, all of the rows inside column A end up in one file, in B end up in one file, C, etc. And this has some quite nice side effects. One is that when we put data into separate columns, we can apply compression very effectively. Columns tend to compress quite nicely. So if you've got a column of country codes, then that's fantastic. It has very low entropy. If you have a column of incrementing IDs, then you can delta encode them very effectively. So that's kind of quite nice. But also, when we actually want to do a query, most notably, we don't need to pull all of our data from the disk subsystem. We only need to selectively take the columns that we need, or the columns that we're interested in. So that reduces the amount of I/O. So another interesting way to think about this columnar database engine thing is, how is this different from me just having a sort of traditional database and then adding an index onto every single column. Because it sort of seems kind of similar, right? An index is a little bit like a column. So how does that differ? Well, the answer to that is to do with this second point here. That in a columnar database, one of the most important factors is that all the rows exist at the same offset within the file. So that allows us to get, and the reason for that is it allows us to get very good merge performance when we bind these data back together. So a columnar engine is basically always doing a merge join. Any operation it does, it always ends up having to do a merge join. So as well, assuming that you're looking at least 2 columns at the same time, which you're likely to do. So that brute force approach is all about optimizing for the minimal amount of data transfer and the most efficient merge join when we get data to the CPU. So our third approach is brute force by column. So less I/O, because we're going by columns, we're only taking the columns we want, we've got compressed data so that we're actually moving less data off disk. We're holding data in row order, which means we can do things like merge joins via this row ID very efficiently, because they all have the same ordering within the files. And then we can do some sort of clever stuff like using predicates to operate on compressed data if we're using a sort of low-cost compression mechanism like delta encoding, and then some other tricks we can do around materialization. So those are kind of 3 approaches to storage engines, and as I said, it's really these different approaches which help us to characterize the different technologies that we choose when we start to bind different data technologies together. As in, it's these which characterize their efficiency for different workloads. So Kafka, which is a messaging system or a message broker used for big data, Kafka has a very efficient disk structure. That's actually one of its core advantages. One of the core reasons for using Kafka is that it has this sort of O of 1. It's O of 1 for reads and writes. And the reason is that it looks a lot like a big distributed file. That's effectively its mode of operation. You have an offset, you jump to a particular offset in the file, you scan for a while to get some messages, you go away, you keep your offset, you come back again. It's a little bit more complicated than that, depending on which API you use, but effectively it's the same thing. So it's really about doing something very, very simple, but very much leveraging for sequential I/O. It's kind of one of the ways that Kafka manages to scale. So lots of other technologies use the index route, right? So just putting the indexes into memory. Riak, MongoDB, Rabbit. A lot of these approaches and this simply because this is a very good approach to take. But remember, it will be limited if the indexes end up overflowing onto disk. So a good example of this would be any of these tools. If you put too much data in them, you'll hit this sort of like pretty hard edge of performance, where performance just kind of dives, and that's when you tend to want to sort of switch to a storage engine which has a more disk-optimized format. So definitely for memory-centric workloads. So not surprisingly, the big data tools, HBase, Cassandra, RocksDB, etc., these things tend to use LSM trees. So that write-optimized storage engine, which allows us to write very well, very efficiently sequentially to disk, and use some tricks to optimize for reads. And these will work with very low, or relatively low memory footprints when compared with the amount of data that they're storing. And then finally, the columnar approach is used by tools, a lot of relational tools like Redshift or ParAccel or any of the sort of standard columnar databases. But also it's used inside the Hadoop ecosystem using the Parquet storage format. So if you're using any of the SQL on Hadoop platforms, like Impala, etc., a lot of them will opt for this kind of disk structure and storage engine simply because of its applicability to analytic workloads. And again, it's because analytic workloads tend to be table scans anyway. You tend to have to scan a lot of the data in order to do some kind of aggregation. So that was a bit on storage engines. Now let's think a little bit about parallelism. So there are kind of two options, there are sort of two ends of the parallelism spectrum. The first one is a fairly well-known one, which is consistent hashing. And this is just the concept that sits behind key value stores. So the idea of getting some data and spreading it across a set of machines, spreading it across a set of shards, and this is a really beautiful pattern for data storage. And the reason is that it's totally linearly scalable. It's actually pretty much the only pattern that is truly linearly scalable in kind of all of the core metrics. So if we add another machine, we'll get a proportional amount of throughput and a proportional amount of storage and a proportional amount of processing power. So key value stores are very, very efficient. They're really just distributed hash maps. But they're somewhat limited in terms of what they can do. So if you've got a key value store shaped problem, then that's a really good solution to take. Then the other kind of core pattern is broadcast, right? So very simple, divide and conquer. And this has been used by data technology since Teradata back in 1986. And it's a very good way of utilizing a large number of machines to solve a problem. It doesn't provide particularly great concurrency because effectively it's utilizing a large proportion of the resources on your cluster at any one time. So one of the interesting things with these patterns is if we look at problems that kind of sit in between those two extremes. So a good example of this is secondary indexes. And secondary index is just saying, if I have a key value store, I might store things by my user ID, and I'd quite like to look up values by name. And that's kind of quite a common thing to want to do. So to do that, you need some kind of secondary index on name. And there are a few different ways to do this. You could have some kind of index on another machine. That's something that some tools choose to do. Another quite common approach is just to put the indexes on the nodes. But the problem with using a secondary index is that it pushes you back to this broadcast pattern. So if you have a sort of very large cluster of 100 machines, you just need to be very aware that as soon as you use a secondary index, you are executing all of those machines at the same time. And that has an impact on your scalability. So you've fallen out of that beautiful sort of key value store, consistent hashing scalability niceness. So yeah, that's more just of I guess, a kind of note of this balance. So this pattern works really well when you've got a long-running job. If you're just looking somebody up by name, it's not that it doesn't work, but it has a different. It certainly won't scale with the same properties. And then probably the often sort of overlooked term, which is really important when you actually want to scale a platform or a single platform to a large number of users, is replication. So replication is actually often used by many stores for resiliency, right? So you have a replica somewhere else just so that you can kind of get back to a nice state if you lose a machine. I'm not really going to talk about that here. That's kind of a different concern. But what I'm going to talk about a little bit is just the idea of using replication for scale, because in a data platform, you kind of need both primitives. You need primitives for replication and for sharding. If you have one, it's not that you won't work, but there will be certain eventualities that you won't be able to solve. So really, you want to have primitives for both. And the reason for this is actually going back to that broadcast pattern. So that if we're broadcasting requests to all machines, then we have a concurrency limit. So replication is a very simple way out of that problem. It actually creates some other problems, but it is a very simple way out of that problem. So just going back to the 1990s, you would have a relational database, you would have a clone of that database that sort of ran in the background, maybe you did reporting of it, that sort of thing. It's the same concept, right? It's just the concept of having multiple copies of the same data and using that as a way of distributing load. So the point is you need both. So replicas isolate load, so very useful if you've got a kind of broadcast paradigm. It also provides redundancy, etc. The problem with replicas is you have to kind of keep them in sync. And that leads you down to this sort of consistency issue, which was made popular by Brewer's CAP theorem. Who's familiar with CAP theorem? Okay, we've got a few. So CAP theorems, I'm not going to go into CAP theorem too much, but what I will simply say is that if we have a number of replicas and those replicas become dissociated from one another in some way, then we will have a hard time maintaining consistency across them. And that's because consistency in a distributed system is actually a really difficult property to create. It's a difficult property to create, and it's arguably impossible in the face of arbitrary partitions. But actually, automaticity and ordering, so particularly when you think about a traditional relational database, they were originally designed with this in mind, right? How can I keep your most precious commodity, as safe as I can? And yet, despite the fact that most of them run on a single machine, and this is the thing that they kind of value the most, many of them don't implement serializable. Certainly, or many of them don't implement serializability at all, which is the sort of it's the one level of consistency which really guarantees what you would conceptually expect consistency to be. Or certainly atomicity and ordering, in terms of effectively making it look like writes appear on a single thread. So if we put this into a distributed world, then it gets even more expensive. It's even harder to manage. So one of the solutions out of this is effectively the single writer principle. So it's just the idea that we would consolidate all our writes into a single place. So if we consolidate our writes here, then it's kind of easier for us to manage that problem, and then we can push those writes to other machines, which we can then use to read from. And that's actually, it's kind of clever. It's like avoiding the problem. Avoiding a problem is actually a really good way of solving a problem if you can work that into your use case. So there's a pattern, one of the patterns which sort of promotes this idea is this thing called CQRS, which is command query response segregation, which is an extremely simple idea. It's simply, and it could be summarized in this context as simply splitting our writes from our reads. So we have a command come in, and we would write that into something which is write optimized. Right? So this might be an LSM-based approach. And then we'd have a process that would effectively denormalize it into a read-optimized form. So in a relational world, you might denormalize. In a non-relational world, you might do some pre-computation, or you might switch it to a different format like Parquet. So by separating command and query, we're able to get better performance because we've isolated our consistency concerns, but we're also able to use different underlying data formats. The big problem with this pattern is that you kind of can't read what you just wrote. So you wrote something in here, and there was a bit of period of time, and then it became visible. And that can be somewhat limiting in some use cases. But there's some quite nice tools, sort of more contemporaneous tools, which use these approaches under the hood and give you a nice abstraction on top. So Druid's quite an interesting database. Anyone come across Druid? So it's like an analytics engine. It's kind of cool. It's quite relatively new. And it does exactly this. It just provides an abstraction over the top. So you have a real-time node, and that real-time node is not surprisingly optimized for fast writes, and have a history node. Data propagates from one to the other, and Druid simply, under the covers, queries both of those for you. It gives you a consistent view. And that's actually quite a nice way to be able to sort of scale a difficult problem. So you can do this. You can do this without using a single tool. You can do this inside a data platform. Really by just applying the same principle. So in an operational analytic bridge, we have data coming in, and what we're really doing here is we're splitting the mutable from the immutable. So we have something which is effectively going to buffer writes and deal with consistency concerns. So if we have multiple users trying to update the same value, we're going to concentrate that, we're going to concentrate that workload within this layer. Then as soon as all writes come in, we'll offload them into a stream. And that's going to create effectively a journal, a log of all of the mutable changes in the system. And then off the back of that, we can create a set of views, a set of different instances, which could be in different technologies, but most likely are actually going to have certainly different data sets inside them. And we can query those. So the big deal here, or the big difference between this and the previous approaches, is really just that idea of trying to separate the mutable from the immutable. Because when we have an immutable stream, we can leverage replication. It's very hard. Like, as soon as we leverage, if we try and use replication inside something which has to provide a degree of consistency, then we have a kind of difficult problem to solve. Certainly if you want to provide ACID properties, like full ACID properties across sort of multiple values within our database. But by splitting it, the mutable and the immutable, we get this really nice area at the end, which we can just kind of like, we can have multiple replicas. And that allows us to scale things quite nicely. And then finally, by using a stream processor, or by using a streaming system to create this log, we can use a stream processor to allow us to respond quickly to changes as they come. So one of the problems with a lot of relational databases is they kind of tend to be kind of black boxes. It's very easy to get data into them. Well, it's relatively easy to get data into them. But it's very easy to ask them questions, and it's relatively hard to get data out. It's certainly very difficult to get a relational database to talk to some other media. So there's some quite nice concepts here, certainly from the perspective of scaling. It's mutable data at the front, where we'll generally shard, immutable data from the stream backwards, where we may shard or we may replicate, but replication is just going to be much easier because the data is immutable. So another architectural pattern is the Lambda architecture. So the Lambda architecture is effectively a batch workflow architecture, which has got a bit of extra cool stuff added on the side. And there's a kind of a good reason for this. So a lot of Hadoop platforms or Hadoop data flow platforms will have a pattern where they just effectively ingest data, they push data through a range of different forms, come up with some kind of the results that they require, put them into a serving layer so that people can query them. That's kind of a very typical pattern. And one of the problems with this is that the batch layer can take quite a long time. So at some companies, this can actually this can get into like many hours, more than 10 hours in some cases. Certainly, it's hours. So one of the solutions to this problem is to add a streaming layer around the side. And there are some advantages to doing this. So firstly, in the streaming layer, we can use a couple of tricks to get a faster result. Firstly, because we're in a stream processing platform, we're going to effectively use a windowed view of the world. So that's not going to give us exactly the same results as the batch layer, but it will give us something that's likely to be quite useful to our users, or hopefully is going to be useful to our users. And there's a couple other tricks that we can use to get good results inside this fast streaming layer. But then the streaming layer writes to the serving layer, so we have a flow of data coming in here. And then the batch layer will just catch up at some point when it eventually gets around to it and give us the right result. So this kind of architecture works really well if you're operating on data that's basically immutable already. So if you're using, if you're aggregating log files have the advantage that they don't change. A log file is a log file, or an entry in a log file is a log file, and no one ever updates that value. So these work really well with immutable streams of data. But the Lambda architecture has some issues because the streaming layer and the batch layer are effectively separate. And that means you kind of end up often having to dual code. There are some ways around that with sort of dual purpose engines these days. But if you end up sort of doing these as completely separate layers, you often end up having to dual code your problem. And that can be a maintenance problem. So there's another approach which is termed a stream data platform. And stream data platforms are quite often used with Kafka. And this is where you take all of your data in. So it's a bit like the Lambda architecture, but rather than having a batch and a stream processing layer, it makes the assertion that you can solve most problems using simply a stream and a sufficiently powerful stream processing layer. So you're doing the same thing. You bring all of your data in, your analytics run inside your stream processing layer, and then off the back of that, it will create a bunch of different views, which you find useful for different tasks. So this has the advantage of obviously being a lot simpler for a start, but it also has the advantage that it's kind of keeping data moving, right? So this idea that we want to kind of keep data moving in an organization is quite powerful, because really, I think because of the long history of relational databases, we've often kind of got caught up in this idea of just get some data, we have to persist it, and then we'll do some queries on it later. And that kind of batch pattern goes back many years, and it's kind of slow. Whereas if we take this kind of approach, then effectively we're always dealing with data as soon as it arrives, right? And we're keeping it moving and passing it on to another layer of processing. And that's quite an attractive idea. So the reason I put Kafka in there is that Kafka is actually a really good choice for doing this, because Kafka has it doesn't really care if you leave data inside it. And one of the things that you need to do in a stream processing layer or in a stream processing system is, you don't really want to be checkpointing to some database all the time to maintain your state. It's very useful to be able to sort of process in a distributed way, and then if something goes wrong, well, you can always just go back and recreate your state. So that's a more powerful approach than checkpointing. And we can also use this kind of pattern to, so rather than, those two patterns are really kind of big, classic, big data flow patterns. But we can also use this pattern for streaming or stream processing within an organization. So this is a little bit more like sort of typical typical sort of enterprise integration. But it's quite an interesting idea. So in this kind of approach, we would use something like change capture. So a program which reads the transaction log of a database and turns that transaction log into a stream. And there's a number of these available. So the Confluent platform has some connectors which are quite good for this. There are other ways of doing it too. But this is kind of really a nice idea. So we often have state already inside our relational databases, so we can use those to manage consistency concerns in a nice and isolated way. But then we can sort of liberate the data from these various different silos into one large stream. And then we can operate on that stream using a set of stream processors and create a number of views off the back. And again, we're trying to promote this idea of splitting the mutable from the immutable. Right, so a lot of our power from this point forwards comes from maintaining immutability. As soon as we start breaking that and we start changing things, then it all kind of falls apart. And the key for doing this in practice is actually about being able to firstly assert correctness, and secondly, ensure repeatability. So that's to say, we need to be able to regenerate our state from effectively a sort of arbitrary point in time. That's what we want to be able to do. So yeah, so that's kind of a nice approach for sort of more kind of traditional data flows. So things we like. We really like treating state as an immutable stream of data. So be it from a storage engine perspective, right up to sort of big data or company architectures, this idea of a log, this idea of just appending rights to an immutable stream that captures all of our facts, is a really powerful idea. Secondly, we like the idea of not just having something on disk, but something that we can react to in real time, listening to all of the state changes within our system, as well as being able to sort of observe them. We also really like this idea of being able to replay things that happened before. So rather than having to constantly checkpoint stuff to some media so that we can kind of get our state back, the idea that we can read stuff from a messaging system, and we can go back in time and recreate our state again, both from the point of view of regenerating state, but also because it means that if we're creating views, so let's say we're creating a view of a data, a view of some particular form of data in a real company, it's really nice to be able to create something that's just small enough to solve the problem that you need to solve. That's a very agile approach. But if you're going to create something small, then you need to be able to expand it later. And to do that, you need this degree of replayability. So replayability is or ability to recreate state by effectively replaying from this log is also, I think, a really powerful idea. And we like the idea of avoiding or isolating the immutable from the immutable. So we want to this really difficult problem of sort of circling around state. We want to confine that to the smallest bounds we can and leverage the immutable world and the replication that comes with it. And that in turn allows us to basically read optimize, both from a storage engine perspective or through sharding or replication. And then we like the idea of having both primitives for both sharding and replication so that we can achieve this. But most importantly, the kind of tricky thing is being able to reason about time. And this is the sort of the crux of this problem, is that whenever we create a system like this, which involves many versions of the data across different replicas, we have to have some way of coordinating them. Certainly if processes are going to read, particularly read from multiple different sources. So reasoning about time, that's a bit of a trickier one, and is not particularly well solved yet. And finally, it's this idea of blending a whole set of tools to create or to focus specifically on different problems that we need to solve. And that's it. Thanks very much. The slides on the internet if you're interested, and if anyone has any questions, I'd be welcome to take them.